Swayam Prabha. Digital India. Educated India.
Welcome to the third lecture of the sliding contact bearing. In this lecture, we will first study the mathematical modeling of the hydrodynamic bearing, and we will derive the Reynolds equation and find the equation for pressure distribution along the clearance space of the hydrodynamic bearing. Thereafter, with the help of that equation and the other charts given by Raimondi and Bondi, we will find different design parameters related to the hydrodynamic bearing, and later on we will see also the case of transfer of heat from the lubricating space, because that is also important, because that heat is not removed, then the temperature of the lubricant may increase and that will lose its lubricating properties, and thus the bearing may fail. So, let us start the mathematical modeling of the hydrodynamic bearing, the derivation of the Reynolds equation. First of all, we will see some simplifying assumptions, because in the mathematical modeling some assumptions are taken, but those assumptions must be valid, and the equation derived will be valid only under those assumptions. So, let us see the hydrodynamic theory, and for that a bearing is taken which is shown by this dashed line. If you will take it the full journal bearing, and if a partial bearing is taken, then this is the partial journal bearing, where the angle subtended by bearing will be represented by beta. Now, for the case of full bearing, the beta will be 360 degree, and we have journal center given by this OJ, and the bearing center given by OB, and the eccentricity will be E, and the journal is rotating in a clockwise direction, and so the equilibrium position of the journal is in the third quadrant, and the colored zone is the lubricant or the clearance space, and the line of center is dividing the clearance space into two zones. The first zone where the lubricant is flowing from a smaller area to bigger area, and another zone where the lubricant is forced to flow from bigger area to the smaller area, and thus it will create the hydrodynamic pressure. So one of the important simplifying assumptions resulted from Reynolds' realization that the fluid films were so thin in comparison with the bearing radius that the curvature could be neglected. The clearance space which is shown in this figure is highly exaggerated. This much of clearance is not there, it is very small in comparison to the radius of the journal and the bearing, and so the curvature effect is neglected. And so we can represent the bearing and journal by two inclined plates. This is your bearing surface, and the journal surface will be represented by this, and this top plate which represents the journal surface is moving with speed u, the surface speed u, well, and in between is the lubricant. So this is the result of the first assumption which was taken. Other assumptions made were the lubricant obeys Newton's viscosity effect, and so the fluid which is inside the clearance space is satisfying the Newton's law of viscosity, and the fluid is the Newtonian fluid. So whatever formula we will derive will be valid for Newtonian fluid, where the fluid is satisfying this equation, the shear stress is equal to mu du over dy. If the coordinate is such that along the thickness of the film the coordinate is y. Then the other is the forces due to inertia of the lubricant are neglected. That means the F is equal to ma, so this A effect is neglected. The lubricant is assumed to be incompressible. The viscosity is assumed to be constant throughout the oil film. There is perfect adhesion between the lubricant and the bearing surfaces. That means the lubricant which is in touch with the surfaces have same velocity as the surfaces have. So if this is the case, is the bearing surface which is stationary, so the fluid just adjacent to the bearing surface will have 0 velocity, and the fluid just adjacent to the journal surface will have surface velocity equal to the surface velocity of the journal. Using Reynolds assumption that curvature can be neglected, we fix a right-handed XYZ reference system to the stationary bearing. We now make the following additional assumptions. The radial clearance is so small that the pressure gradient across the clearance is neglected. That means pressure gradient will be only in the circumferential direction and in the axial direction. Along the radial direction, along the thickness of the lubricant, the pressure variation is neglected because of its very small size. Thus, the pressure is independent on y coordinate. The velocity of any particle of lubricant in the film depends only on the coordinates x and y. So, with this we have a shaft which is rotating with speed n, and within the clearance space the fluid which is shown by dots, a fluid element is taken, and the coordinate system is such that the circumferential direction is taken as the x, this is the circumferential direction is taken as x, and the radial direction is taken as y, and perpendicular to the screen will be the z, which is visible in this front view of the bearing. So, in this view the length of the bearing is visible. This is the length of the bearing given by L. This is the length of the bearing, and the fluid element is somewhere here. So, radial direction is y and axial direction is z. So, the coordinate system is taken in such a way that the radial direction is y, circumferential direction is x, and axial direction is z. Well, the diameter of the shaft is d, which is shown here, and the fluid element is taken at an angle theta. This is your theta, and along the journal center the radial load W is acting, and the fluid film thickness along the element is h. Now, with this we have a infinitesimally small element here, and in the xy coordinate system the xy plane in the plane of x and y. In this plane, we are drawing the fluid element and showing all the forces which are acting on this fluid element. That is shown here. This is the fluid element which was taken in the clearance space, and the coordinate is x and y. X is the circumferential direction, y is the radial direction. And in this plane, the forces which are acting is on the fluid element with dimension equal to dx and dy. The dimension of the fluid element along x is dx, along y is dy, and along z is dz. This dimension will be dz. Okay. So on the top surface, the shear will act, and on the bottom surface the fluid shear will act, and on the vertical planes the force due to pressure will act. As the fluid is moving in the direction as shown here, you see the fluid is moving in the direction of x. In the direction of x the fluid will move. The movement will be something like this. Okay, and so the fluid movement is along this direction, and you have pressure on this side is given by P, and on this side is given by P plus del P over del x multiplied by dx, and the shear stress which is acting at the bottom surface is tau x, and on the top surface is tau x plus del tau x divided by del y multiplied by dy. So if you are moving a distance equal to dy, the change in shear stress is del tau x divided by del y multiplied by dy. Similarly, when you are moving a small distance equal to dx, the change in pressure is from P to P plus del P over del x multiplied by dx. Now when we will multiply these stresses and pressure with the area on which they are acting, we will get the forces acting on these planes. So the force acting on this direction will be dy multiplied by dz. dz is, this is your dz. Okay, so the force acting along this plane, you may say A, B, C, D plane, will be P multiplied by dy and dz. Similarly, the force acting on the plane E, F, G, H will be P plus del P divided by del x multiplied by dx multiplied by dy and dz. Similarly, multiplying these shear stresses by the area on which they are acting, the area is dx multiplied by dz, dx multiplied by dz, and the area on which this tau x is acting is again dx multiplied by dz. Now, taking summation of all forces in the direction of x equal to 0, summation of all forces in the direction of x is equal to 0 will give you your tau x plus del tau x divided by del y dy multiplied by dx dz. This is acting in a positive x direction, and another force which is acting in the positive direction is P. Is P multiplied by dy dz, dy dz, and in the negative direction the force is tau x minus tau x dx dz minus P plus del P over del x dx multiplied by your dy and dz, dy dz, and that should equal to 0. Okay. Now then you will have this dx dy dz everywhere. This p dy dz, p dy dz will be cancelled, and tau dx dz and minus tau x dx dz will be cancelled. You will have now del tau x over del y dy dx dz is equal to del px dx multiplied by dx multiplied by dy. So, dx dy dz you will get here and here. The volume will not become 0, and so the other term should be del tau x divided by del tau is equal to del p over del x. Now we know that the fluid which is inside the clearance space is Newtonian fluid, and so it will satisfy the Newton's law of viscosity. That means the shear stress which is acting in the direction of x, tau x, is equal to mu viscosity and del u over del y, the velocity gradient in the direction of y. So, substituting this in this equation, we will get del square u by del y square is equal to 1 over mu del p over del x. Now, this is important equation. By integrating it twice, we will get the value of u. Integrating twice, we get small u is equal to 1 by mu del p over del x y square divided by 2 plus c1y plus c2. So, by integrating twice, we have two constant of integration c1 and c2, and these constants of integration can be obtained from the boundary condition. Now, what is the boundary condition for this particular case? In the x direction, the fluid is moving, and the condition is your this is the bearing surface and this is the journal surface, journal or the shaft, and this shaft is moving with velocity u, and the coordinate is something like this. This is your y coordinate, this is your x coordinate. So, when y is 0, then what will be the velocity of the fluid? Your fluid element is somewhere here, and the velocity profile is this one, and we are considering velocity of the fluids in the x direction as small u, velocity of the fluid in the y direction as small v, and the velocity of the fluid in the z direction as small w. So, this u, what will be the value of this u when y is 0? The fluid which is just adjacent to the stationary bearing will have 0 velocity, and so at y is equal to 0, u will be 0, and at y is equal to h, the fluid film thickness. So, at any location fluid film thickness is given by h. So, at this location the when you have moved at a value of y is equal to h, then you will be touching the journal surface, and the fluid which is touching the journal surface will have velocity equal to the journal velocity from one of our assumptions. So, at y is equal to h, u, the velocity of fluid in the direction of x will equal to the surface velocity of the journal. So, these are the two boundary conditions. Applying these two boundary conditions in this equation, we will get the two unknowns, the constant of integrations, and those constants of integrations are by substituting u is equal to 0 at y is equal to 0. When we are substituting y is equal to 0, so this term will become 0, this term will become 0, and u is 0, so C2 will be 0, and C1 is equal to u divided by h minus this one, substituting the second boundary condition. Now, substituting these two C1 and C2 in this equation, we get the velocity of fluid in the direction of x, or the velocity of lubricant in the direction of x, that is the circumferential direction. the velocity by which the fluid will move along the circumferential direction, and that is capital U y divided by h plus 1 by 2 mu del p over del x multiplied by y square minus hy. Now, when you inspect this equation, the velocity of the fluid in the direction of x, it consists of two parts. The first is a linear part. This is the linear, and this is parabolic. Y square term is there, parabolic. Well, now let us see what we studied when we were studying the principle of development of hydrodynamic pressure by considering two cases. The first case, when the plates were parallel to each other, the top plate was moving in this direction with speed u, then the velocity profile was linear. And another case in which the top plate was moving in the vertical direction, and due to that, and this plate was stationary. Now, due to movement of this, a pressure was developed and the velocity profile was like this. And we considered that when there will be wedge type of action or some inclined plate, and this plate is moving with the speed u, surface speed u, then the velocity of fluid can be obtained by summation of this case and this case will equal to this one. So, the velocity of fluid in this case, which is just analogous to our bearing system. Okay, this is the journal surface and this is the bearing surface, and here is the lubricant. So, the velocity profile will be summation of a linear term and a parabolic term, and same thing we are getting here. Let us see in detail. This is the case, linear term, parabolic term, and summation of these two is this one. We have, and then the resultant is shown here, this and this, and the area of this one is analogous to the amount of fluid which is going in, and the area this is amount of fluid which is going out, and it will satisfy the conservation of mass. Both will be same. We now select an element of lubricant in the film of dimensions dx, dy, dz and compute the forces that act on the sides of this element. This is shown here. Now, we next define Q as the volume of lubricant flowing in the x direction per unit time. By using a width of unity in the z direction, the volume may be obtained by the expression Q is equal to 0 to h u dy. That means you have this type of plate, is the direction of x, and the fluid element has velocity equal to u in the direction of x. So, the fluid flow rate will equal to, at any cross section, at this cross section, I want to find what is the fluid flow rate. So, the height is equal to h, that will be the fluid film thickness at that location. Okay. So, when you will integrate this u from y varying from 0 to h, you will get the fluid flow per unit your length of the bearing. Okay. So, in the z direction we have taken unit dimension. So, this plate is having the z directional dimension equal to 1. So, substituting the value of u, just u which just we have derived, which is given by this one, the Q will be after this integration, we will give it by this one. The next step uses the assumption of an incompressible lubricant and states that the flow is the same for any cross section. That means you have this inclined plane, and as there will not be accumulation of fluid, so whatever fluid is coming in, the same will go out. So along any cross section, the flow rate will be same. Here the flow rate area is more, so flow rate will be smaller. As the area is decreasing, the flow rate will increase. So thus dq divided by dx will be 0. Substituting this and integrating, we get du over ds divided by dx minus d over dx h cube divided by 12 mu dp over dx is equal to 0. We have a equation d over dx within the bracket the term h cube divided by mu dp over dx is equal to 6u dh over dx. Now this formula we obtain considering the flow only in the direction of x and taking the element in the plane of x and y. We have not considered the flow in the direction of z, that means along the axial direction, and we know that the shaft will be something like this, and here is the bearing. The bearing is open from its edges, and so there will be flow along this direction, and that is called the leakage. Okay, so let us take that also. Now we are taking a plane z and y. Z is the axial direction and y is the radial direction. And the same thing we have done. Here is the bearing, axial direction is z and is the radial direction y, and in this diagram also the same thing is shown. So the forces are shown to be acting on different planes similar to the previous analysis, and again what we will do is we will find summation of all forces in the direction of z and we will get a equation similar to the previous one. So summation of all forces along the z is giving this one, and finally we have del p over del z is equal to del tau z over del y, and that is this formula. So your del square w over del y square, where w is the velocity of the fluid element or the fluid in the direction of z or along the axial direction. So del square w over del y square is 1 divided by mu del p over del z. Again by twice integrating we will get the value of w, that means velocity of fluid in the direction of z. Okay, so that integration is done and we got w is equal to 1 upon mu del p over del z y square divided by z and two constant of integrations, and again we will apply the boundary conditions. And now what are the boundary conditions? The boundary conditions are for this particular case we have this one, okay, fluid element, and in the z direction there is no flow of the, or there is no velocity of the journal along the z direction. The journal is moving with a surface speed u in the circumferential direction. There is no any movement of the journal along the axial direction perpendicular to the blackboard, which is the z axis. Okay. So in this particular case what will happen is if I am taking any section where the height of the or the clearance or the fluid film thickness is h, the bearing and journal both will have 0 velocity. Okay. So w which is the W, which is the velocity of the fluid, small w, in the direction of axis or the axial direction is 0 at this location, and W is also 0 at this location. So, when, and this is the direction of y, so when y is 0, W is 0, and when y is h, then also W is h. So, the two boundary conditions are this one. So, therefore, the C4 is 0, this constant of integration, and C3 is having this value. And when it is substituted in this equation of W, we got W is equal to this one. Only parabolic term is there, linear term is not there. So, in this case, what will be the what is the case? This is the case of a plate in which the top plate is moving down. The velocity profile will be only this parabolic. This type of flow will be there. This is the z direction, axial direction of the bearing. So, along the axial direction in the both way, and this is the length of the bearing L, okay, and this is your y. So, the flow will be in this way, and that is giving the side leakage. The shaft is there, here is your bearing, this is the direction of z as it is. So, the lubricant which is in between this will leak out from this direction and this direction with this velocity profile. But there will be a pressure gradient also, and that pressure gradient will be this one. So, we have W. Now, we can find the flow in the direction of Z, considering the unit length of the unit width of the bearing. So, that is done here. Qz is equal to 0 to h W dy. So, Qz is this one from 0 to h. Substituting that, we get Qz as equal to this one. Now, the considering the fluid as incompressible, we will have a condition dqz divided by dz is equal to 0. Substituting all this, we get a term given by this one. Okay. Then what we have done is, we have this term and we have previous term when we were considering only the flow in the direction of x. So, this is the equation considering flow in the direction of x, and the another equation is considering the flow in the direction of z, that means axial. Now, adding these two, we get a complete equation, well, which is rearranged to get this one. d over dx h cube divided by 12 mu dp over dz plus d over dz h cube divided by 12 mu dp over dz is equal to this one. This is the second order differential equation. By solving it, we can get the pressure profile in the clearance space, but it can be solved either by finite difference method or your finite element method, or by certain approximations which are short bearing approximation or the long bearing approximation. But and this is also called the Reynolds equation. This is the very basic equation. Later on, by considering other things like we assume that the fluid is Newtonian. By considering non-Newtonian, this lubricant was this Reynolds equation was modified. Similarly, in this while deriving this equation, it was assumed that the flow is laminar, but with the increase in shaft speed, it may become transitional or it may become turbulent. So, later on again this equation was modified to include the effect of turbulence. So, there are certain modifications in this Reynolds equation considering different working conditions, but this is the basic equation. Now, the design considerations. The variables either given or under control of designer are the viscosity mu, because the lubricant which you can take is under your control. The load per unit projected bearing area P, that the W is not in your control. It is as per the design of the shaft and bearing system, but you can and D is also not in control, but by taking the L you can change the value of P and others. The speed is either given, speed will be given, and in this also certain thing will be given. The bearing dimensions R, C, beta and L. Beta will be 360 for the full journal bearing. Now, the dependent variables or the performance factors are the coefficient of friction which will develop, the rise in temperature. If there is certain rise in temperature, due to this rise in temperature, the viscosity of the lubricant will change. Now, with the change in viscosity, the Sommerfeld number or the bearing characteristic number mu n by P will change, and there will be certain change in the operating system, and that may lead to the failure also. Well, so this delta T is also very important, whether it is within our range or not. The volume flow rate of oil Q, the minimum film thickness HO. Now, the Trumpeter's design criteria provides us some limiting conditions. The Trumpeter, a well-known bearing designer, recommended a set of design criteria. That means the minimum film thickness to prevent accumulation of ground of surface particles is given by H0 should be, minimum film thickness should be greater than or equal to 0.005 plus 0.00004 D. D is the journal diameter in mm, and this H0 is also in mm. The maximum temperature to prevent vaporization of lighter lubricant components is, the maximum temperature should be 120 degrees centigrade. If temperature is more than that, then you may go for solid lubricants. The maximum starting load to limit wear at startup, because we have seen that initially when you start running the journal, then it climbs on the surface of the bearing, rolls on the surface of the bearing, there will be metal to metal contact. So, maximum starting load to limit wear at startup when there is metal to metal contact is given by W static divided by LD. This D is the journal diameter, it will be small d, should be less than or equal to 2.0 megapascal. And the minimum design factor or factor of safety on running loads will be greater than or equal to 2. Now, the equation of pressure, which was Reynolds equation, can be solved as we seen by some approximate method like finite difference method or the finite element method. But Albert Raimondi and John Boyd used an iteration technique to solve Reynolds equation, and they published 45 charts and 6 tables of different parameters of the journal bearing. So, we have this part 3 of the charts are included in this lecture. Assumes infinitely long bearings, thus no side leakage, assumes full bearing, assumes oil film is ruptured when film pressure becomes 0. Now, the viscosity chart, that means with the temperature, what will be the value of viscosity? We know that with the increase in temperature, the viscosity decreases. So, for a particular lubricating oil, this type of temperature will be there. So, there is a temperature chart which gives us about the mu. So, viscosity is clearly a function of temperature. Viscosity charts of common lubricants are given in the figures in the coming slides. Raimondi and Boyd assumed constant viscosity through the loading zone. Not completely true, since temperature rise as work is done on the lubricant passing through the loading zone. Use average temperatures to find the viscosity. That means T average will be the temperature of the lubricant which is entering inside the clearance space, and delta T divided by 2. Delta T is the rise in temperature. So, if the bearing system is assumed as a black box like this, then the lubricant is entering inside it with a temperature T1 and it is going out with temperature T2. Okay. So, this difference is delta T. So, the temperature of the lubricant inside the bearing system will be taken as the T average, and that is the T1 plus delta T divided by 2. This will be taken to first find this will be your T average. So, this will be taken to determine the mu. Okay. Now, corresponding to this mu, we will get the Sommerfeld number S, because that is R by C square and mu n divided by P. Knowing all other parameters, now we can find the value of S. Okay. This S will give you the value of rise in temperature. There is a chart which gives us the rise in temperature corresponding to a particular Sommerfeld number. So, again we get a value of delta T, and this delta T will be substituted in this equation again, and we will get the T average, and corresponding to this T average again we will get the value of mu and we will get the Sommerfeld number. And this process is repeated till the successive Sommerfeld numbers are very close to each other, and that Sommerfeld number will be taken finally to get other parameters, performance parameters from the coming charts. This is the viscosity temperature chart. On the x-axis is the temperature, on the y-axis is the absolute viscosity is millipascal second, and different curves are corresponding to the different grade of lubricating oils, that SAE is 70, 60, 50, 40, 30, 20, 10. So, corresponding to any temperature, let us take the temperature 70 degree, then the viscosity is lesser for the SAE 10. Okay? And you need a viscous fluid in the clearance space. So, you may go for this 20, bigger value of viscosity, SAE 30 again bigger, for SAE 70 you have this. Now, curve fits for viscosity versus temperature is also available. You may get the value of mu corresponding to any temperature in degree centigrade by getting the value of mu 0 and this B from this table corresponding to different grade of the oils. Now, notations of Raimondi and Boyd, the polar diagram of film pressure distribution showing notation used by Raimondi and Boyd. That means this O dash was the bearing center and O is the journal center, and there the HO will be there, and the fluid film pressure is given by this one, and this is the location value of the P maximum, and the location of P maximum is represented as theta P maximum, and it is measured from the vertical line. Okay, direction of the load. This is the direction of the load, direction of load. So, this and this is the maximum value. So, this theta P maximum is the angular location of the maximum pressure with respect to the direction of load. Okay. Now, this phi is the angle where the minimum film thickness is there. This is the minimum film thickness. Okay. So again, from the direction of the radial load, this is measured. Then from the direction of radial load, the location of zero pressure is also found, which is given as theta p0. This is the theta p0. This is your theta p maximum. Okay. So these are the notations which will be used in the charts presented by Raimondi and Boyd. So the first chart is related to a performance parameter given by H0 by C. So knowing the Sommerfeld number, these charts are with respect to Sommerfeld number, you may get the minimum film thickness corresponding to different values of L by D ratio. L is the length of the bearing and D is the diameter of the shaft. So L by D is an important parameter. If it is 1, then corresponding to this 1 value, we get a short bearing or the long bearing. If it is equal to 0.25 or less than that, then it is called the short bearing. If it is more than this one, then it is called the long bearing. Okay. So corresponding to different L by D ratio, you will have a curve, and corresponding to a Sommerfeld number and a particular value of L by D ratio selected, you will get the value of H0, and knowing the C, the clearance, you will get what is the value of H0. Now this H0 will be compared with the Trumpler's criteria, because Trumpler has given the minimum value of H0. Then position of minimum film thickness, that is theta. Okay. So here again, knowing the Sommerfeld number and knowing the L by D ratio, you will get the position of minimum film thickness phi. From this curve, coefficient of friction variable RC by F, this RC by F can be determined. So if you have a Sommerfeld number and L by D ratio, you will get this RC by F, and let it has any value, this A, then knowing R and C, you will get the coefficient of friction. Okay, that will be C divided by R multiplied by A, and this coefficient of friction will give you the what amount of heat is generated. Now another performance parameter is the flow variable, which is Q divided by RCNL. It is a dimensionless number, So knowing the Sommerfeld number, knowing the L by D ratio, you will get this Q divided by RCNL. Q is the total volumetric flow rate. Then Qs divided by Q is the flow ratio. That means this gives us the side flow, and this is the leakage flow divided by the total flow. Knowing the L by D ratio, again L by D ratio and Sommerfeld number, you can get this. Then P divided by P maximum, knowing the Sommerfeld number, L by D, you will get this one. Then in this figure, you have a Sommerfeld number and different parameters are there. Along this axis is the terminating position of film theta P0. So if you remember, the pressure distribution was something like this. So from the direction of radial load, this location was obtained, and this angle was your terminating position of film theta P0. So knowing the L by D ratio, you can get the theta P0, this theta P0, and along this axis is the position of maximum film pressure. So along this is the maximum pressure, P maximum is along this, and so this angle you can also obtain from this diagram. Now the lubricant temperature rise. We know that in the sliding contact bearing, due to sliding action, we do some work on the lubricant, and it rises the temperature, and that is shown here. You have a journal and the bearing. The lubricant is supplied at a temperature T1, and it is returning back at a temperature T1 plus delta T, where delta T is the rise in temperature of the lubricant when it is flowing through the clearance space. And the total supply of the lubricant in the clearance space is Q. Among this Q, Qs amount is leaked out from the axial direction, and the flow rate of leakage is given by Qs, and the temperature of that lubricant which is coming out from the side is also rise in delta T, and the average temperature is taken, that is T1 plus delta T divided by 2, and the temperature of the lubricant which is coming out returning will be T1 plus delta T. Now if a control volume is taken, the sum, all these fluids are going, this fluid and this fluid is going in a sump, where the lubricant will be cooled and the foreign particles are taken out. Then again it is pumped to the here. So this return is coming to this sump. This is also coming here, and it is going out. So this control volume of the sump is shown here. Lubricant at a temperature of T1 and flow rate Q is going out from the sump, and the lubricant which is coming in is this one, Q minus Qs at a temperature of T1 plus delta T, and the side leakage Qs, lubricant is also coming in the sump at a temperature of T1 plus delta T divided by 2, and there will be some heat loss because you will cool the lubricant, because it is coming at a temperature more than the T1 at which it should again go to the clearance space. So there will be some heat loss. So on this control volume, when we will apply the equilibrium, then we get heat loss, the balance, energy balance. Energy balance will provide you this heat loss, and the heat loss is given by this formula. And in this, capital Q is the volumetric oil flow rate into the bearing, which will be mm cube divided by second, and Qs is the volumetric side flow leakage rate out of the bearing and to the sump. It is also in mm cube per second, and Q minus Qs is the volumetric oil flow discharge from annulus to sump, and it is also given in mm cube per second. Ti is the oil inlet temperature equal to the sump temperature Ts, and delta T is the temperature rise in oil between inlet and outlet, and it is in degree centigrade. Rho is the lubricant density kg per meter cube, and Cp is the specific heat capacity of the lubricant joule per kg degree centigrade. Now using sump as a control region, we can write an enthalpy balance. Using Ti as the enthalpy datum temperature, we have heat loss given by rho Cp Qs delta T divided by 2 plus rho Cp within the bracket Q minus Qs multiplied by delta T is equal to rho Cp Q delta T, and within the bracket 1 minus 1 by 2 Qs divided by Q. Now also the heat loss can be obtained from the Petrov's equation, and that is 4 pi PRL capital NCRF divided by C divided by J. Now comparing these two, we have rho Cp delta T divided by 4 pi P is equal to Rc divided by C, within the bracket 1 minus 1 by 2 Qs divided by Q, and within the bracket 1 minus RCNL. The previous equation is arranged in such a way that we have the performance parameters as per the Raimondi and Boyd charts. We have RC divided by F chart, we have QS divided by Q chart, and we have Q divided by RCNL chart. So, for any Sommerfeld number, we have these values. For common petroleum lubricant, the density will be 861.5 kg per meter cube, Cp will be 1764 joule per kg degree centigrade. Therefore, rho Cp delta T divided by 4 pi P, substituting the values, this rho Cp and others, you will have, it is this value, or this is given as 0.12 delta T divided by P. So, 0.12 delta T divided by P is given by this, okay, and this you can get from the different charts of the Raimondi and Boyd. There is a chart for this, there is a chart for this, there is a chart for this, and we have a separate chart also with respect to this 0.12 delta T divided by P with respect to the Sommerfeld number, and that is given here. So, along the y axis is 0.12 delta T divided by your unit bearing load in megapascal, and along the x axis is the Sommerfeld number. Knowing the Sommerfeld number, knowing the L by D ratio, you can get the temperature rise dimensionless variable, and from that you may get this delta T. So, in one of our chart, we were discussing about which temperature is to be taken to determine the Sommerfeld number, because all these charts are in terms of Sommerfeld number. Okay. So, for that we had taken T average as equal to T1, the inlet temperature, plus delta T divided by 2, and corresponding to that we got the value of mu, and corresponding to that we got the Sommerfeld number. Okay. Now, this Sommerfeld number will be used here to get the new value of delta T. Okay. So, again we will have a new value of delta T. So, again we will find the T average, okay, from this formula. Then from T average we will get mu, from this we will get Sommerfeld number, and this Sommerfeld number will be again used here to get the value of this delta T, and this delta T will be again used in this equation, and we will repeat this till the two consecutive value of Sommerfeld numbers are almost same. Then that Sommerfeld number is the operating Sommerfeld number, and this will be used to get the different performance parameter, that means RC divided by F, Q divided by QS, or Q divided by RCNL, and others also. There is a formula, the interpolation formula for the Raimondi and Boyd, knowing the L by D value and knowing the value of parameter, that parameter may be RC by F, or it may be Q divided by RCNL, or anything, any variable which is given in the y axis of the Raimondi and Boyd. So, if that value is known to us for a L by D ratio is equal to infinity, what is the value of y? For L by D ratio is equal to 1, what is the value of this particular y? And this y will be this flow variable. So, you can use this formula also to get the your variables or the performance parameters corresponding to a particular L by D ratio. Now, there is a self-contained bearing. In this case, in which the lubricant carries away all of the enthalpy increase from the Journal-Bushing pair has already been discussed. Bearings in which the warm lubricant stays within the bearing housing will now be addressed. These bearings are called self-contained bearings because the lubricant sump is within the bearing housing and the lubricant is cooled within the housing. These bearings are described as pillow block or pedestal bearings. They find use in fans, blowers, pumps, motors, for example. Okay, so let's do this. This is the formula. The heat given up by the bearing housing may be estimated from the equation, this equation, where Q loss is equal to heat dissipated. U is the overall heat transfer coefficient considering radiation and convection, and A is the surface area of the bearing housing. TB is the surface temperature in the housing, and T infinity is the ambient temperature. So, this U overall heat transfer coefficient can be obtained considering different conditions from this, and we have a formula for Tf minus Tb, fluid temperature minus bearing temperature is alpha multiplied by T bearing temperature minus the outside temperature. So, bearing temperature is not known, but the fluid temperature and this is known. So, we can get this in terms of that one, and finally we may get what will be the bearing temperature, that means Tf plus alpha T0 and 1 plus alpha. Now, in beginning a steady state analysis, the average field temperature is unknown, hence the viscosity of the lubricant in a self-contained bearing is unknown. Finding the equilibrium temperature is an iterative process wherein a trial average film temperature and the corresponding viscosity is used to compare the heat generation rate and the heat loss rate. An adjustment is made to bring these two heat rates into agreement. This can be done on paper with a tabular array to help adjust Tf, the full temperature, to achieve equality between heat generation and heat loss rates. Because of the shearing action, there is a uniformly distributed energy release in the lubricant that heats the lubricant as it works its way around the bearing. Okay, so we have this Tf is equal to Ts plus delta T, the same as the previous one. Now, the next thing which is related to the radial clearance and different values, this outside temperature of the lubricant coming out, H0, Q and H. So, how with the radial clearance, these values changes. The flow rate increases with the increase in radial clearance, the outside temperature decreases, the H, the heat generation is also decreasing with the increase in it, but the minimum film thickness is first increasing and then decreasing. So, this zone is found as the most appropriate zone. With this, this is a particular question which may be solved using the analysis which has been done. So, with this we are ending the module which was for the analysis of sliding contact bearing, and in this way in detail we studied how to design a sliding contact bearing with help of Raimondi and Boyd charts. Now, if in a particular case you do not want to use this Raimondi and Boyd charts because they gives us some approximate value, you can solve the Reynolds equation by finite element method or the finite difference method, and you may get the pressure, and that pressure will give you some other values, and that will be very appropriate one. So, with this we are ending this module, the sliding contact bearing. Thank you.